So, ready to start? Okay, so today we are trying to write a very simple two-dimensional stencil application using C++ and HPX for parallelization. So what we want to do is we want to solve this partial differential equation. Disclaimer, what's in the repository in the examples, it's not real math. It's mostly ignoring the discretization, so the step width between the different grid points. So if you look at the result, it's 10 to the power of 279. So it's a little bit too big, but it doesn't really change that. It doesn't really change the computation. So essentially, what you do is you'd add a factor or two, and to get the damping. So essentially the distance between the different grid points. But anyways, if you would like to add real math, it shouldn't be hard to do it actually, hopefully. The boundaries of the PDE are a constant 1, and we want to use high-level modern C++ and want to avoid loops as much as possible and use algorithms instead. Okay? So the first slides will be on how we would model this to actually be usable and have some nice high-level abstractions to work with the grid and to iterate over and to apply the stencil. So what we want to do is we want to store the grid in a vector of doubles. So we want to work with double values, and we have nx grid points in x direction and ny grid points in y direction. Okay, so it doesn't have to be a quadratic grid. It can be any rectangular shape. Okay, so since we want to store it in a vector, we are dealing with contiguous memory. Okay, so that means that the first row will begin at the 0th index, right? And then the eth row will be at the I times nx index, and the last row will be ny minus 1 times nx, right? The starting point. So that's how you would address the different rows in your grid. Okay, so just simple linearization of your two-dimensional point. Okay, I think everyone's familiar with that technique, right?
Stored as a vector.
Hmm?
Why not store it as an array?
STD array?
Yeah, for example.
If we'd store it as an array, we would have to do constant sizes. So we just use the vector to have the dynamic memory allocation. Okay, so we just allocate the memory once, so it doesn't really matter. Okay, and we for the sake of the example and experimenting with it, we want to dynamically be able to change the size. So that's why I choose a vector. You might also ask, why not just use a double pointer and use new and delete manually, right? Valuable. That's some choices people do as well. But we are using C++, right? And in modern C++, manual memory management is not really needed anymore. That's why we can just use the vector here. And the goal is really to not have any performance penalties. And with modern compilers, you usually don't have any performance penalties over a raw double pointer when using a standard vector. So it's really essentially the same, unless you use the add member function. So the vector overloads the square bracket operator, right? So you can use it as if it was an array or a pointer, right? And that comes at almost no cost. Same as iterators, right? The iterators of a vector usually map directly down to the pointer. You just don't have to fiddle with the dynamic, with the raw pointers. And in addition, if you compile in debug mode or with some address sanitizers or anything like that, you also get additional checks. So if you run out of bounds, you get a runtime error immediately. So it's very easy to actually verify that what you've coded is correct when using those higher level abstractions, right? And to complete it, if we want to access the elements in the row, well, we just do the linearization again, right? So if you want to access an element with x coordinate equals I and y coordinate equals y coordinate equals I and x coordinate equals j, then we just have to apply this formula here. Okay, so just basic linearization of the two-dimensional point. Okay, if you would, you're free to store the memory in row major order or column major order, right? It doesn't really matter. It's just a matter on switching the indices and choosing the right dimension, right? So if you would interface with Fortran, for example, you would want to use the column major order. Okay. So what we want to do is we want to iterate over the grid within our application domain of this Stencil update, right? So what I chose in this example is I wanted to update line by line, right? And each line needs the upper row and the lower row, right, in order to do the 5-point Stencil update. So it makes sense that we iterate, that we write two iterators, one that's going over the different rows, and each of the rows can then yield an iterator where we can access the line, right? So, right, so if we want to do the line update, we just write a template function. We don't know how the iterators look like yet, right? So we want to have an iterator that marks the begin of a line and the end of the line, and the iterator that where we store the result, right? And this function, the signature of the function, is very close to a signature of a function you'd get from the standard library, right? If you remember the transform example from yesterday, you had a very similar interface, right? You had the begin and end iterator and the result where you want to store it. Okay, so in this example, we advance the result iterator by 1 at the beginning and at the end, just to skip the boundaries, right? We have constant boundaries, so we just want to skip it. And then for the begin and end, for the begin we want to skip the first, and we want to skip the last as well, right? And then we just iterate over our line iterator. And, well, it would be nice if the line iterator would have members that denote the upper line and the lower line, right? So we can easily index it. And when we do the so when we advance the iterator by 1, right, it would be nice that it would just move along element by element and move the upper and lower neighbor along inside of that operation, right? Everyone's fine with that? Cool. So who thinks this is going to get you a performance penalty? Yes, sure. But I mean, performance penalty with respect to if you would just pass in 3 pointers. Okay, but sure, yeah, but that's more or less the property of the algorithm, right? So to get rid of that performance penalty, we would do some kind of cache blocking, right? But that should not be the scope of this tutorial. I just want to focus on the interface. But what's nice though is that with that interface, you can easily implement cache blocking, right? So, right, you would just pass in different begin and end iterators. You would have to adapt a little bit because if you do cache blocking, you don't want to advance in the beginning and the end, and you want to pass in the correct boundaries already.
Is your image correct? So you do one block and so in your image you sum the corner elements, but really you sum upper and down elements. Is this correct?
Should be correct, yeah. So we
You add upper and up, plus one down, plus one left.
yeah,
right.
it's not modeling the exact mathematical equation. It's just saying what do I need to have.
Image in the image you sum the corner.
Yeah.
Plus one. No?
So we sum. So up -1, right, is, now let me show it on the laptop with the cursor. So up is pointing to here, right?
Yes.
And then -1 is that. Okay. +1 is that.
But then it's really not the algorithm written on the second slide, right?
Is it not?
It's essentially a plus. It's a cross, right? The first page you have x -1, x +1, y -1, y+.
Yes.
Right?
Right.
So the one you have there is an x basically. So it's x +1, y +1, x +1, y -1, etc. If I understand correctly.
So
It's a different stencil, that's all I'm saying.
so that one here is that one here is y -1,
Yeah,
x -1.
yeah, exactly.
Oh right.
So it's not,
Yeah.
not what you have in the second slide.
Okay. So
It's a different stencil.
you're correct, right? Typo in the slides. Sorry about that. But thanks for. Absolutely, yeah. Sorry about that. Yeah, but it shouldn't really matter in the actual for the sake of this tutorial. Sorry about that. But thanks for noticing. Okay. As a disclaimer, I'm not really a mathematician. It's just something I made up, really. Okay. Right. So this is how we want to do the stencil update. If you want to apply a different stencil, right, it should be possible, right? Using that interface. So, right. So I think it's feasible and applicable that we make the stencil hierarchical, the iterators hierarchical. So one iterator that iterates line by line from row to row to row to row, right? And and once we have that row iterator, we want to yield something where we can access the elements in this specific line, right? So the row iterator would move by nx and the line iterator by +1, right? So we can just jump ahead the different lines. And what we gain here from that implementation is that we save multiplications for the indexing, right? So we just really do only additions. So that's really nice, a really nice property. So how would it look like in C++? So, well, the line iterator, so moving element by element, right? We would need the iterator for the upper line, the middle line, and the lower line, right? And once we want to advance element by element by element, we just increment the iterators or decrement them, or we can even, since we are dealing with random access data structures, we can even advance by n. We can write it completely generic and using the std advance functionality, then we wouldn't have any limitations on the iterators we put in. So we could even put in lists or anything if you feel like it, right? But the problem here is that this isn't the interface that you'd expect from an iterator, right? And it wouldn't really work with any algorithm at all. So writing or conforming to the iterator interface is a little bit difficult. You always mess it up at some point in time. It happens to me all the time, essentially. So that's why we have this thing called iterator facade, which does all the boilerplate code generation for you, right? And it's conforming to the CRTP pattern. I mentioned it because I saw it on your flipboard here. So if you revisit the slides from the C++ course, right? This is the CRTP pattern. So you pass in your own type when deriving from the iterator facade. Then you want to pass in the value type, so the type you get when dereferencing the iterator. And of course, you want to say which iterator category you want to conform to, right? And then to make it complete, you also want to have the an equal function, which just says is the iterator equal to another. You want to be able to dereference the iterator, and you want to be able to compute the distance from one iterator to another. And by deriving from that class and implementing all the functionality that I showed on this and the last slide, you have a full-blown iterator that you can use in any standard algorithm you want, including the parallel algorithms. So that's a very nice utility and very nice property of this iterator, right? And I think if you use this iterator concept, you gain a lot, right? So you gain a lot because you can easily reuse what's already there, right? And this line iterator is a domain and application specific adaptation of that iterator concept, right? And it was fairly easy to write. I'm sure you have to think about it when you want to write an application, and it might not be the first thing that you think about when writing such an application, right? So I just want to make you aware of those iterator concepts and that they are very nice and well easy to use and write and implement. And so I mentioned debuggability, right? I can really test this iterator in isolation. I can add debug code in all those different functions. I can really make it bulletproof so that if anybody uses it wrongly, right, it can easily be caught by asserts. So that's another nice property. And yeah, we also want to have the row iterator, right? It's a little bit more complicated. So for the row iterator, I said we want to move row by row by row, or line by line by line. So we have to pass it an additional nx parameter in its constructor. And in order to construct the upper and lower neighbor of that row, we need to subtract or add nx here, right? So that we are one line up or one line down, right? And the value type here is the line iterator. So when we dereference the row iterator, we get the line. So we can compose a really nice hierarchical algorithm to work on our stencil, on our grid, right? And the addition here is that I needed, so the iterator facade has additional parameters so that you can overwrite the reference type that you get when dereference the iterator. So it's a little bit hand-waving because for the row iterator, we don't return a reference but a new value, right? We don't want to store the line iterator all the time and want to advance it each time we advance the row iterator. So that's why we want to, when dereferencing the iterator, we want to yield a new return a new value to the line, right? If you would omit that, you would get a compile time error saying that you can't form a reference to a local variable. Right, and so advancing is then very similar to the line iterator, instead by moving just by one element, we move by n times nx elements, right? And that's how we just advance the upper, middle, and lower row, row by row by row. Okay? Is everybody happy with that? Questions?
Can you go to Line Iterator?
Microphone. Microphone. Where's the microphone?
You repeat the question and I'll look for the microphone.
Oh.
Lovely.
Okay, so Line Iterator is, so it's a child, or let's say it's inherits the HPX Util Iterator facade,
Mm-hmm.
which takes as a parameter Line Iterator. How should I read this? So Line Iterator is a derived class of iterator facade, but iterator facade accepts Line Iterator class
As a template parameter.
as a template parameter.
Right.
So
Did you attend the C++ course?
No, but
Okay, so as I said, the iterator facade provides you with all the boilerplate code for the iterator interface, for the standard iterator interface, right? So, for example, the iterator facade would have something like the operator star, so you can dereference the iterator, right? So maybe operator star isn't a good choice. Operator plus plus, right? Where you advance the iterator and return the new value, right? The same iterator, okay? So, okay? Now, what's the return value? You don't want to return iterator facade because that would be a different type, that would be the base class. So you would need to have some kind of virtual functions or anything, right? Which would be costly at runtime, right? So you really want to, when you do this operator plus plus, you really want to return the real iterator that you defined, okay? So that's why you want to return the derived class, okay? And that's what the first template parameter is, right? So we pass in the derived class as a template parameter. So we can use the type inside of this base class to do some operation. And that's called the curiously recurring template pattern, CRTP. I think you covered it in the C++ lectures, didn't you?
I'll explain it to Anton in depth if he requires it.
Okay.
Okay. Should we look at the code? Okay. Any other remarks or questions? Okay. Good. Clock's ticking. Right. So the complete code, of course, can be is linked. Again, I forgot to link to the line iterator. Make a note, please. Right. So let's move on. So the initialization is, well, we just say which data type we want to use. In that case, the std vector, right? And we want to have two vectors, right? So we can use the old values to update the new values, right? So it's essentially the Jacobi iteration scheme that I want to use here. And yeah, we just, so std array doesn't initialize its members, right? So you have to explicitly initialize them. You can do so by assigning to it or use the initializer list syntax in C++ with the curly braces, right? I chose the assignment to the elements here. And then you just call the init function where you initialize your boundary conditions and the interior and things like that, right? Okay. And what we can do then is we construct our row iterator, right? So our row iterator takes the standard vector double iterator. So in the repository in the examples, I defaulted the template parameters for the middle and down iterator. So you only have to pass in one iterator because that's the common use case of this iterator. We will get to another use case when we introduce the distributed version. But yeah, once you have the iterator, you construct the current and the next iterator. So that means our current grid, which we want to use to update the next grid, right? And if you would write the code in plain C, you would probably use an index or something like that and swap the index between 0 and 1 all the time after each iteration. We use the iterator and std swap here, right? And yeah, just swap back and forth. And then we just iterate over the rows, skip again the first row and the last row, right? And for each row, we dereference the row iterator, pass it to our line update function, right? The begin and the end. And that's it. And that's how we that's one possibility how you can model such a stencil inside of C++ using, well, modern C++ facilities.
So let's say that you want to run the stencil in the GPU with CUDA, then you have problems because as the STD namespace is the STD is not really supported by CUDA. So I think you have to implement similar things, or is it a problem that you faced?
Actually, no. So I haven't implemented the stencil for the GPU, so I haven't tried that. But actually, no. So the line update is what would go on the CUDA device, right?
Okay. See. Yeah.
So and it doesn't have any STD namespaces.
Yeah.
So
okay.
so you would just slap the device attribute to that function, and you can run it immediately on your GPU.
Because the swap was on the CPU side, the STD swap.
Correct. Depends on how much you want to. I mean, if you would run it on the GPU, right? So first of all, NVCC starts to support more and more of the standard facilities. Right? There's still some problems, but you get more and more and more on each iteration with the compiler. Second, if you would use device memory to iterate over the grids, right? And pass those into the iterator. So as you know, a pointer is an iterator as well, right? So you could just do CUDA malloc and pass in the pointer to the device memory, right? And then what you'd probably do is the for loop and the swap would still execute on the host, right? So no problem there.
Yeah, the swap could be also. Yeah, the swap would be on the host. Yeah.
Right. So you'd only do the computation on the GPU,
yeah.
right? And this here, it's almost trivial to offload to the GPU. Right?
Yep.
You can try it at home. It should be no big deal to do that. So you can either do the complete line update in one kernel, or think of something different. But should be very easily possible.
Okay.
So I don't see a limitation. And you could also use the compute vector that I introduced yesterday, and use the NUMA executor to actually offload this code to the GPUs.
So in the containers, which are the HPX containers, there's no. So the only thing that one has to do is to replace the STD container with a HPX container and the allocator and this device keyword, right?
Right. So in the repository, you have an example for making this algorithm NUMA aware. I won't cover this today in depth. It's on the slide. We can go through the code if you like. But it's really just a few lines of code you need to change.
Yeah, thanks.
Yes, please.
So this is a really nice example. What the numerical analyst would really like to do is to define the point update as one task and then superimpose the dependency graph on top of that and say, well, I need to know all the elements which are to the left and down, right? And then you get Gauss-Seidel, that's a different algorithm. Or, you know, as you've described it, it's basically Jacobi. Now that would be really cool if you could formulate it that way. The point update is one task. But my question is very simple. If I do that, that's only like for floating point operations. From what I understood yesterday from John, that's insufficient size of a task. That is not going to perform very well.
Exactly.
So you have to do a line update, which makes it a little bit less elegant for a numerical analyst.
That's true. Very much so. So from where I come from, so if you'd parallelize that with OpenMP, you would probably only parallelize the outer loop, right? Not the inner loop with the point update, right? So you have a similar situation there.
Yeah.
You don't parallelize the inner loop because for the very same reason of grain sizes, right?
Well, it's a loaded question because I'm thinking in terms of grid tools, and this is what they're trying to address. They're trying to say, well, formulate the point update as the functor, right?
Right.
Then everything will be taken care of behind the scenes. And it would be cool if HPX had something similar to offer. Oh, here's the point update, it's a task. Oh, here's the dependency graph. But as I understand, that's really not going to work because it's not going to perform.
Depends. It could work. So let's stretch that a little bit, okay? So I mean, what I showed so far is just plain C++, plain standard C++, right? It's no magic, just C++. But what we could do in the line update to satisfy your needs is we could easily add a third parameter that's a callable object, right? And that would and that could be used to actually model the point update, right? Okay, and then instead of writing the stencil down here, you would just call the your functor with the iterator or with the dereferenced iterator or whatever, right? And you as a numerics guy can then just provide the point update. Of course, it needs to be a little bit more sophisticated with the iterator because you would probably want to have different stencil types, like not only across and different width and height of the stencil, different dimensions and everything, right? But that.
I think the thing which would be cool is to make it a task.
Okay.
Make it a task, and then you could superimpose different dependencies on it, which would give you different algorithms, right? That was what was behind my idea.
Right.
So I don't know, maybe we should talk about it at coffee if you could somehow simulate that.
Yeah,
or make it totally like small grain tasks.
Yeah. So just a small remark. You don't want to, as you said, you don't want to have one point update in a single task, right?
But I think this question comes because inside grid tools, what's happening is that single point task is being expanded out, and so there's some template metaprogramming going on, which is then unrolling all of those iterations. Now, that could, in principle, be put inside like a meta task object, which would collapse those mini tasks in the same way as grid tools. And if those two libraries were fused in some way, then you'd get the best of both worlds.
So you really need another layer, another DSL layer.
Exactly. Yeah.
Okay, good, good. That's good. Let's talk about it over coffee.
Okay. Good. Any other remarks or questions? Okay. So, right. So next thing we want to do is to add shared memory parallelism, right? So we have our nice and compact formulation of our stencil. So if we go back the slide, we have this for loop, and well, it makes sense to parallelize that for loop, right? And so, of course, the answer is use a parallel algorithm, right? So the question is, which one? Any ideas? So it's a trick question because I haven't, the algorithm that I'm going to use is not really part of the standard parallel algorithms library. There's unfortunately no parallel algorithm that would suit our needs because what we do with this result iterator is we don't move it along, we don't advance it one by one, but we advance it row by row by row, right? So we would really need some kind of iterator that some kind of algorithm that allows us to model that. And this algorithm is called for loop. It's very similar to a regular for loop, right? So you can pass it begin and an end, and you can also pass it some induction variables. So if you look at the code here, the result is kind of an induction, right? At each iteration, here implicitly, we advance it by one row after each iteration, right? So instead of assigning the result of this line update here, I could have put it with a colon and then say result plus equals result plus nx, right? Result plus equals nx, right? And just advance it by nx each iteration. Okay, so it's the advancement of this result iterator is induced by the loop iterations themselves, right? So, and that's what the for loop is able to provide you. So, and this is how it looks like. You have the begin and the end of your iteration, and then you have the induction. So the induction is called every time your loop does another iteration, right? So, and the signature for this induction function is very simple. You pass it any value, which can be an iterator or an integer type or whatever. And the documentation is actually pretty pretty exhaustive. So each time this induction iterator is incremented, you can increment it by a given stride, right? And in our case of this result, we have a stride of nx, right? So we always want to advance it by nx elements. So this comes in very, very helpful. Okay. So
am I right in saying that the induction variable loops have been proposed for a future standard?
yes, you are.
They've been proposed for, it's either 17 or 2. Oh, it's there. Okay. Sorry.
So it's been proposed. I have a link in the slides to the actual proposal of this functionality, so you can get an idea of how this looks like. So this is the complete proposal. It has a little bit more. It also has reductions and what have you not, right? And this is a proposal for 2020. 2020. However, I was asking how good are the chances that this will get in. Unfortunately, doesn't look so good. However, we won't remove it from HPX. I found it extremely useful, right? Especially for those stencil cases, right? Where you where it's very, very easy to write those stencils, because one big difference to the other algorithms is that in your lambda or function that you provide for the element update, the element function, you don't get the value of the element, but the iterator to the element, right? So it's very easy to perform neighborhood calculations inside of that function of that for loop, right? So we have the iterator here and not the value that that iterator yields. So if you compare it to a for each algorithm, what you would get is the value of the element, not the iterator to that element. And that's one of the biggest differences, and also the reason why the standards committee people don't like it, because it's a little bit of an outlier to the rest of the standard algorithms. And exceptions are never good, right? But we won't remove it. So that's nice. And the message here is those algorithms are nice because it's very easy and very compact way of actually adding parallelism to your code, right? And that's really the message I want to convey here. If you have a code and you want to speed it up, well, use a parallel algorithm. With OpenMP, you have the very same mechanism, right? If you have a for loop that takes 90% of your time, well, slap a OMP4 in front of it and be happy, more or less, right? And a very similar pattern applies to the parallel algorithms. Just think about your problem, think about how you might be able to generalize it, and if one of the standard algorithms suits your needs. So John, for example, uses a lot of the standard algorithms in one of his visualization tasks, if I remember correctly. So you might want to ask him about his experiences with those algorithms, if you're interested in more. Okay. So, what time is it?
It's almost 10.
When do we have the break?
10:30.
10:30, great. Excellent. So, of course, as you mentioned, we have, well, kind of a problem because the algorithm as shown here is bandwidth limited because we have all those different cache lines we need to access, right? And we have, in this algorithm, we have 32, we need to transfer 32 bytes per iteration, per element update, right? And only have 4 or 5 floating points. Okay, it's 32 because in order to write the value, you have to get it. So you get the latest version. So you have to update the cache line. Anyways, right? So it's memory bound. Okay, so memory bound problems. Well, you have to make it NUMA aware, right? And question: how do we make it NUMA aware? Right. We just essentially change the policy and the data structure and apply the data locality and execution locality. Right. So getting the NUMA targets, create the right allocator, create the right data structure, right executor, and create the parallel execution policy. Right. And the solution then looks almost the same. I mean, the iteration over the, so the actual stencil computation is basically the same, right? The really only difference is the type of the execution policy. And everything else stays the same. And the type of the iterator, of course. Right? But you can see that the compute vector data structure really implements the very, very same interface as std vector and can be used in the very same fashion. And that's another beauty of this iterator concept. It can be adapted to any data structure that has the right properties, right? That yields the iterators with the correct properties. Questions?
Let's say that I have my own container and I make it look like an HPX container or STL container, and I want to make it NUMA aware. Would it be sufficient that I use the HPX allocator, and what else can I do?
Yeah. So you can roll your own allocator, of course, to make it independent of the parallelization strategy that you want to employ. Or you can just use that, right? So
the thing that I would have to do would be to reuse one of the HPX allocator and something else. So that's
for example, yes, that's mostly it. No, so
okay.
the NUMA placement works with the first touch policy, most by default. So you can change it with the NUMA CTL command, right? Where you can say instead of first touch, I want to have interleaving of the pages, so I have a nice uniformly distributed memory layout, so I don't have to do anything. Usually that doesn't give you the best performance, but it's at least a start that's very non-intrusive to your program, right? Or you exploit the first touch policy. The other option is to use platform-specific APIs to actually bind the pages that you allocated to specific memory locations. But that's a little tedious because if you're working with a regular data structure and it might not be page boundary aligned, so you have to fiddle around with it a little bit. So the first touch policy usually works, is the easiest solution, so to say.
Okay, thanks.
But yeah, the message here is that if you use those higher level constructs, then you don't really have to re-implement it again yourself. Right. Any other question? Okay, so what's missing is to create a distributed version of this algorithm. Right? So what we have so far is just an algorithm that works nicely on a shared memory system, and later in the debugging and profiling session, we will go through the examples and show the different performance properties of it, and go through how good it actually performs, and do. Huh? No? Okay, and do some measurements and stuff. Okay, but what we want to do next is we want to write a distributed version of the program. Okay, and essentially what we need to do is we need to synchronize. So if we distribute the grid, we need to into various partitions. We need to synchronize between the updates of the different partitions, right? So you have the different partitions distributed in the system, and you can't just unsynchronized run the updates on each partition for each iteration step, right? So you have to have some kind of synchronization. I listed two possibilities that you might employ here. So the first possibility, and probably the easiest first shot possibility, would be, well, we have one main thread of execution, and we just spawn off the tasks to all our nodes and do the line update, and once they're ready, they return to our root, and then we do the swap, and then the next iteration, right? So that's implicitly synchronized algorithm. The problem is that we have one root, right? One master worker. And that probably won't scale to a large extent, right? Because the single master will very fast become the bottleneck, right? Even if you do some clever tree branching or whatever, right? If you have a single master that controls the flow of your algorithm, then you will end up with scaling problems. Okay, but you can still do it. It's a nice exercise to get used to the API, right? And get used to the active messaging concept and the actions and whatnot. But I won't cover that here. What I want to cover is the neighborhood synchronization. So every locality will do the same proactively, and just synchronize with its upper and lower neighbor. Okay, and what I want to use there and introduce here is the channel object, which allows you to do this synchronization. Okay. Oops. But I want to do a small detour first to make the tutorial a little bit more complete, to show you actually how to write your own components if you want to. Because the channel itself is a component, right? So even if you use this object, you implicitly use components already. You just don't realize it because we abstracted it away in the API. And that's what I want to show you here, right? I want to construct a hello world object on a given locality. So I say find here, so it's the locality I'm on, and I want to call a remote procedure call to that global object. Okay, the global objects in HPX are called component. So that's the goal of the small detour. Okay. So the component implementation itself, you see the CRTP pattern again, right? So if you want to write a component, you have to write a class that derives from this component base and pass in its own type again for this CRTP pattern to work, right? The single reason to use this CRTP pattern is to really have the compiler through template instantiation generate code for you, right? And don't have to resort to virtual functions and polymorphic base classes, because that's costly, right? So by deriving from that component base, you essentially say, okay, this is a component. This class can be used as a global object. Okay, so we want to do something with it. So we define a function. It's just a print function, okay, which just prints out hello world. So very, very simple function, very dull, not exciting, just for the sake of demonstration. And in order to call that function remotely, we need to adapt this function to an action. Okay, that's needed because in C or C++ you can form, you can have function pointers, right? So you can form pointers to a function which you can then use to actually call that function again. And you can do that for regular free functions or member functions in a class. Okay, so you get a pointer with the address of the function in the compiled binary. The problem here is that this address is not guaranteed to be unique across different processes. Okay, so across different processes, across different binaries, it might differ from when you have different optimization levels and so on and so forth. So if you want to send a function with a function pointer to a different locality, right, or to a different process, then it's not portable and not advisable to send the function pointer directly, right? You have things like dynamic relocation, address space randomization, etc., which just gets in the way and places your function on a different address, right? So what this macro does is essentially it adapts this function pointer of this print function to an action, and this action is then be usable as your remote procedure call. It does some template magic in order to have it work, but essentially what it ends up with is that you create a class a template class with a member function pointer, which derives from a base class, and then you're able to send a pointer to the base class over the network. So our serialization layer supports marshalling of base pointers with derived classes, and the actions automatically get an ID assigned, so you don't have to send large strings or anything, but just a numerical ID when you call the remote action. Okay, that's just the machinery that we use at the moment. So theoretically, this macro wouldn't be needed. It's mostly there for compatibility reasons. So some of the when we started, the older, mainly Visual Studio compiler didn't really grok the take the function pointer and put it into a template syntax. So we had to do some additional magic there. But nowadays it's very portable with modern compilers. So you don't necessarily need the macro here. We still advise to do so if we decide to change the implementation. Then if everybody uses that macro, it's very easy to just exchange it silently. Okay. After we defined our component and defined the actions that we want to expose for that component, we need to register the component to the runtime. The reason for that is that components are created by using a factory. Okay, so you have to register the type to the factory so that you instantiate a component on a remote locality. You only give it the ID of the component, and then the correct class will get created using a factory utility. And the reason you want to use a factory is that you have plugins. Right? You can have plugins dynamically loaded, so you don't have to have the same binary on all processes, on all processes that you run, but have different implementations of different components, etc., and so on. So you have to use a factory in order to realize that, in order to implement that, and that's why you need to register components separately. It's a little bit of boilerplate. You have to use a macro again. That's just how it works. Once you've done that, you might want to consider registering the action. That's not mandatory. The only purpose you want to register the action is to make your code portable. To make your code portable across different compilers. So for example, one use case that we support and that we have a demo for is that you have a simulation running and then you attach a visualization to that simulation. Right? And that simulation process can be run on a Windows machine, on an OS X machine, on an ARM machine, or whatever. Right? And it might have been compiled with a different compiler on a different architecture. So if you don't register an action, you just take a very implementation-specific define. So implementation-specific means the implementation of the compiler. Take the string out of which the ID will be generated, right? And the string might change from compiler to compiler. So one thing we noticed, for example, is when the C Nights corner came out, you even had different strings when going from the host compiler to the CN5 cross compilation. So usually you don't need to register the actions. But if you do heterogeneous runs, heterogeneous applications, it's advisable to do so. Okay. Now we have the components. So if you remember from yesterday's overview slides, if you allocate a component in the global address space, you get an ID type back, right? And the ID type, as I mentioned, is very similar to a void pointer, so not very type safe. So currently what we try to do to make the ID types type safe is that users can, again, that's not mandatory, it's just an optional thingy that also makes your code a little bit more readable. So they can define clients to the component, which can be used to interface with the object living in the global address space. Okay, so what we do here is we derive from the client base class. Again, it's the CRTP pattern, right? And we have to say which component we are a client of. Okay. And then in the constructor, we can just instantiate, we can just allocate the component in the global address space. We get the ID type of where to allocate that object, and then just create the new object in the global address space, right? And then the base type holds the ID type, and we can use it to schedule actions to that global component. That's why we write the print function. Right, and in the print function of the client, we just call the action. We call it with async here. Another nice property of those clients are that you can model the behavior on how you want to call the actions, right? So you don't necessarily have to return a future here, but you can just return a void and make the call to the action synchronized. So the print action really only returns when the action has been completed. So that's completely up to you how you want to write your client function, the interface, how to interface with the component. The channel component that I'm going to introduce uses a specific techniques and overloads its client functions with the launch policies. So you get different behaviors and different return types based on the launch policy that you pass. So either be it apply launch policy or async launch policy or sync launch policy. But we will get to that later on. And then we're done. We reached our goal, right? We can create an object of this client. In the constructor, construct the new global object, and then call a function on that global object. Question?
I was just going to say that yesterday when I said I love components, I've gone off them again now. I should point out that in the example that he's going to show you, all of this boilerplate disappears because there's a wrapper which just produces an object which he's going to use. So you don't normally have to do all this, but this is sort of an extra layer of stuff you can add to make things. Well, when you see the stencil example with the channel, you'll understand, so I'll just leave it at that.
Yeah.
What's the alternative to components if you don't like components?
Well,
there's none.
If you have an object on a remote node and you need to invoke an action on that specific object, then you really need to turn it into a component so it's got a unique ID. But if you have a global function on a remote node, then you just make an action which calls that global function. You don't have to bother with any of the components. So none of the examples, I mean, I've never used a component properly in any of my codes because all of the codes I've worked on have had, they're sort of adapted MPI codes which have got an int main, and they basically do everything globally on that node, and they communicate with other ones. And as long as you only have to communicate with another node, and you don't have to communicate with an object on another node, If you know, as long as you don't have to have a specific, there's multiple things you have to choose between them. And you can get away with having your own little indexes sometimes. You can send her a global function and just say index 1, 2, 3. And if there's some global data on that node, you can interact with it that way. So components are really when you want to abstract things away into a much more, well, I mean, he would say in a much more C++ kind of way, because you have individual objects on nodes and you want them to communicate with other individual objects on other nodes, and this allows you to do that.
Mm. Since you mentioned the MPI stuff and the global state, so that's one alternative if you have global state, right? So, but yeah, if you like it, use it. The other nice thing about components, I mean, they're just C++ objects. One way of using them is certainly to use them as if they were their own rank, right? So you mentioned those old MPI programs which have their global state. So one way how to use components would be to encapsulate that global state in one object of a component, right? And then you have a component that models your MPI rank, right? And you can then have multiple of those components, right? And you can write domain-specific communication functions using the actions, right? So you don't have to have MPI send, MPI receive, or whatever. You just can say, give me the boundary, or whatever, right? And by having that, you abstract away the notion of processes completely, right? And you can just instantiate a bunch of components wherever, and then your algorithm just works as if it was an MPI process, right? So by using that technique and remembering what I said yesterday in the overview, that you're able to migrate components transparently, you can oversubscribe your node completely by instantiating tens or hundreds of those components. And when you run into load imbalance as well, just move them away to a different node, right? Just as a line of thought. Isn't it beautiful?
No, I just remembered that I have used components in one of my programs, and that made it really nice. But that was one particular example, which I don't know.
Okay. How much time do we have left?
Not enough, so get talking. Talk faster.
I want to allow the attendees to catch up. Okay.
Stuff has sent them to sleep, so
Yeah.
move on to the exciting.
I apologize. I hope I didn't turn you away. So now let's use those clients, right? So what's the channel? A channel is an implementation of this whole component interface thingy, right? And a channel is essentially, so you have the future and the promises, which are just which are essentially a one-shot channel. So you can stuff one value in and get one value out. And a channel is a multiple-shot future, so to say. So you can set it multiple times, and each time you set it, it increments its generation, or you can pass the generation you want to have by yourself. So each time you set it, you set it with a value and a generation, right? And this setting buffers it, right? And it buffers it until you get it again, right? And you get it with the same generation, and that's how you would do your neighborhood synchronization. So you set the boundary on one node, and you get it on another node, right? And this might even happen between different processes. Okay, so you can set it multiple times and get it and get a result multiple times back. So unfortunately, we don't generate our documentation out of it yet. So that's why I said use the source. The source code is sometimes very nicely documented. So in that case, it is not. So here you see a small example of how we'd write such an interface to a component. So you see that the channel is indeed a client base. So that's actually linked to the master repository of HPX. So you see that the channel is indeed a client base. So it is a client to a global object. And you can look at the various overloads for the get function, right? And if you have an async launch policy, you get a future back. Can you read it in the back?
Yeah.
Good. So if you have an async launch policy, you get a future back, right? If you have a synchronous, if you have a sync launch policy, you get the immediate value back. So that allows you to have a very nice interface so that you can that users of that class are able to use it depending on their own needs, right? And for the setting, you have similar overloads, right? With one addition, the apply policy. So that's something I haven't talked about yet. So when you do call a function asynchronously with, say, async, you always get a future back, right? And if the task happens to be executed on a remote node, that the result of the function needs to be transferred back to the caller, right? So you have an additional message there if you call a remote function. Even if it's returning void, you still have to signal that the function completed, that the function returned in order for the caller to be able to synchronize on that asynchronous function call. One optimization that we have here is the apply policy. So you can just apply, just launch the function, just spawn it without getting any synchronization possibilities back. So it just returns void or bool in that case. So it just returns nothing, and it's a fire and forget invocation of that action, which just does, yeah. So the only guarantee that you have here is that it will get executed eventually, but you don't know when, but you don't care in your algorithm. And we're going to use that exact apply policy inside of our example, right? So do you have an idea of how this might be used? Right, so it's very similar to MPI send receive, right? So the get is kind of a model of send, and receive is a model and get is receive essentially, right? But instead of a tag, we have the generational counter, so you can differentiate between the different invocations. So you can really have one-sided communication here, right? You don't need to synchronize with your other remote end. Right.
How is it implemented underneath the hood, or do we want to know?
It's implemented with a map. So the question was, how is it implemented? You can look it up. But the implementation is that you have a map, which is a binary tree, and for each generation, you have one entry in the map. Okay, and each map entry is essentially a promise. Okay, and when you try to get the value, you retrieve the future from that promise for the respective generation, right? And then you set it, you set the value of that promise for that generation. And the map is used to buffer mismatched getting and setting. So you don't set or get something that hasn't been set and don't run into deadlocks.
Is it lightweight?
Yeah. It's, so the lookup of this promise is done with a log n complexity due to the binary tree implementation. I want to look into making it an unordered map, so we have a constant time access, amortized constant time access. But usually I haven't actually measured it, but I think you only have only a few in the order of 10 elements in that map at all time. So it's really...
Actually, you have the number of elements that have either been set or get. So if you set number 4 and I haven't got it yet, then it creates number 4 and sets the promise. And if I try and get number 5 and you haven't sent it yet, it creates the promise on this end. And then when you push number 5, it effectively... So there's only... The map holds the exact number that have either been sent or are waiting to be received. So if you send 0, then 0 gets created, and then I get 0, and then 0 gets destroyed. And then he sends 1, and I get 1, and there's 1 in the map. And if I try and get 2, but 1 is still in the map because he hasn't sent 2 yet, then what will happen is 2 gets created, and so there's 1 and 2 in the map. And so it basically, it expands or shrinks according to how many sets and gets have been applied to it.
No.
And one of the optimizations that I'm actually working on now is to do, you'll be able to limit that map and register it as an RDMA one-sided window buffer so that one side can effectively put stuff directly in, and you'll have a kind of circular buffer that rotates around so those things are set and get. And that will make it even more efficient.
If you have a great load imbalance and have one producer that constantly sets something to the channel, your memory consumption will grow and grow and grow and grow if nobody gets it again, right? But if you have a nicely balanced problem, like the stencil problem, right? It's very nice. So the current implementation is unbounded, so to say, right? So you can really fill up the memory with the channel. But it shouldn't be that hard to actually write a bounded channel. So you only are able to buffer 2 or 3 or 4 elements in there.
And then you would have a choice on either the sending or receiving end, that if the buffer was getting too full, you could either throw an exception or you could block.
All right. Okay, so it more or less models the I receive and I send API functions of the MPI standard. So, yeah, it's one complaint that we got a lot, that how do you do this neighborhood synchronization? It's so easy to do in MPI, right? So that's our attempt to it, and it's also something that I want to demonstrate today. So another nice property is that once you have the global objects, right? I mean, what you get back when you allocate a new global object is essentially a globally unique identifier to that object. So if you have your big distributed application running on 1,000 nodes, right? How do you exchange those ID types between the different ranks, right? And the answer to that is by symbolic names. You don't actually pass around explicitly the ID types, but you use the global address space layer to actually help you to distribute your and help you to set up your communication and synchronization patterns that your application needs to use. And that's what the symbolic name registration is for. So the API function that I'm going to introduce in this tutorial is the register with base name functionality, where you are able to register an ID type with a base name and the rank. So what you end up with is a name that's constructed out of the base name plus a numerical identifier for that object you want to register with, right? So in that case, we want to register our channel that we just created with a given base name and a given identifier. So I called it rank, right? So, and on a different locality, you can find from that base name again and have it construct and have it a reference to this channel that you registered the base name with to, right? So you can very easily, without any explicit communication, exchange your neighborhood information that your application needs, right? And I also put down the link to the documentation of that API function. So you have a few more API functions in there. I showed you the this function here, find from base name, where it takes the base name and the identifier and returns the new client or the client representing or the client that this name resolved to. You can also find all from a given base name. So where you just give in the number of the components you registered with that base name, for example. Or you can register a... It's not there. I'm looking for a specific function where you can register a vector of ID types. Anyways, those are the API functions that you can use to actually register names and resolve the given names to a specific client again. Okay, and that's all we need to set up our communication pattern in order to be able to synchronize between the different partitions. Do you have questions? Okay. The symbolic namespace, so the facility in the AGAS service that manages the symbolic names and does the resolution of the symbolic names to the actual IDs, to the actual global identifiers, is a distributed system, as well as the resolution of the ID types to the actual locality and the local virtual address. Is also a completely distributed system. So using those functionalities does not limit scalability of your program because it's a distributed database that scales with your number of localities that you have. Okay. I'm almost through.
You're over time.
Hmm?
You're over time now, actually. So
Should we make a break or just continue? Just continue. Okay. Oh, what do you want to do? Continue. Okay, so the communication between the partitions. So, right, if you have an upper neighbor, you want to send the first row up and receive the last row from your upper neighbor, right? And if you have a lower neighbor, you want to send your last row downwards and receive the first row of your lower neighbor, right?
did you explain that you're parallelizing along the y-axis so that you're doing stripes of, so each node has a stripe of data along the y-axis, and that's why he's using up and down.
Right. The spatial decomposition scheme is striping, just for the sake of simplicity. I don't want to impose that striping is the optimal partitioning scheme there. It is not, because the boundary layer doesn't scale very well when you increase the problem size. Right? So if you write a real application, then you would want to use a different partitioning scheme, but you probably know all that. So it's just for the sake of simplicity to not overwhelm you with code that's just for the boundary exchange. So just exchanging the just exchanging boundaries with the upper and lower neighbor is good enough as a first approximation. So in full code, I actually can you read it? Mm. So for the example, I wrote another abstraction which I called communicator, which does exactly this boundary exchange, right? So I use a channel, and I love templates, obviously, right? I use a channel of type T, and in the constructor of the communicator, I give it the rank of this partition and the number of total partitions that I want to have, right? And next thing I do is that I have the base names for the up and down, right? And then I set up the channels. So I only need to set up the channels if my number of partitions is greater than 1, right? If I have just one partition, well, yeah, I don't need any communication at all. So I just save the setup there. And the case where we have an upper neighbor actually is when our rank is greater than 0. So rank 0 is at the top, so we don't have an upper neighbor, right? So if we have anything greater than 0, then we need to set up our communication strategy so that we are able to get the last row from our upper neighbor. Yeah. And so what we do is we find the channel from our upper neighbor, rank -1, right? Upper neighbor. And our upper neighbor sends us its last row, so it sends downwards, right? So from the upper neighbor, so when we want to receive from our upper neighbor, we want to get the value of its channel, which points downwards. Okay? And then in order to send our first row, we create our own channel and register it with the up name and our own rank, right? And the real beauty of that code is this is completely asynchronous. There's no blocking involved here. This constructor returns immediately. It's all happening behind the scenes. And the first time you use the channel, it blocks until the ID types got delivered. But the reason why I highlight this, that it doesn't block at all, is that you are able to completely abstract away the asynchrony, all the features that you use in higher level APIs. So you don't see any mentioning of features at all anymore. The code's nevertheless, the code is completely asynchronous. It's completely hidden behind the scenes. For the sake of completeness, for our communication to the lower neighbor, we do the exact opposite, right? So if we are not the last partition in our distributed application, we want to, when we receive from our lower neighbor, we want to receive from its first row, right? So we use the up name to find the right channel. And in order to send down, we use the down name and construct exactly here, right? And then we have the helper functions. In the algorithm, I want to check whether I have a neighbor to the lower end or to the upper end, right? So I just want to check it real quick, and then I want to set or get respectively. And here you see that I use the apply launch policy, right? So the setting returns immediately. So I can immediately continue with my application, right? Because when I set the channel, I don't need to have any synchronization. The synchronization is only important for getting the value, right? Because I need the upper boundary to do my line update of my first row, right? But setting it to my neighbor doesn't need any synchronization. Yes, please.
The definitions of receive and send at the bottom there, they're standard arrays of channels. Those are not futures to channels. So
No.
those are actually a concrete instantiation. But when you said that in the constructor, when you call set and you receive and you set up the send and receive, that's actually blocking effectively there.
No.
Why not?
No, because the client is very strange data structure. Well, not strange, but a special data structure, because it is like a shared feature to an ID type.
Oh, okay, because it's
So
based on client base. When you
So it is essentially a feature to an ID type, just a different name, essentially. But so we have a lot of trait classes to classify the different objects that we have, and the client base is classified as a feature. And the value that it yields is an ID type. So you can use a client as if it was a feature. You can attach continuations to it and things like that. Okay. Okay. Let's move on and do questions maybe after the break, huh? Or does anybody have concrete questions?
So I guess it's the data you send on the row is coalesced, right? If you have to send the other boundary, maybe you don't have like data with strides. Do you have to pack it in a buffer and then unpack it, or yeah, do you have to do that?
Sure. If you have I don't know. More advanced partitioning scheme where you have rectangular partitions which don't have to be full stripes, then yes, you would have to pack your boundaries up and send them respectively.
The user does it, and or is it there's some API to?
There's no API for that, because there's so many data structures out there, so many different ways to pack up the boundaries, and you probably have it already for your MPI codes. Because you need it there as well.
Or you could send two pieces.
Or you could send two pieces.
Different channels for each piece. Or you could...
Yeah, right. So if you would have multiple boundaries, so top, left, right, down, for example, you would probably set up 4 channels, right? But still you would need to pack the boundary, because it's not contiguous anymore in memory. Okay, almost done. So let's write the first distributed version of it. So in order to update the first row boundary, what we do is that we check if our communication has an upper neighbor. And if it has an upper neighbor, we do the boundary exchange. So first of all, we get the boundary of our upper neighbor, right? And once we have that boundary, we have in the row iterator, I forgot to show you, we have the top boundary helper function, which creates a row iterator such that the upper line points to the newly received vector. Oops. Right? So we receive the vector which contains the line, the complete line, and we use that as our we use that in the iterator to point to the upper neighbor, right? So we essentially, if we are at the top, right, the up iterator would point to an invalid memory location, right? And if we would dereference it, we would run into a seg fault or any other diagnostics that come from the iterator interface. But what we do with the top boundary function is that we replace this up iterator with the begin iterator from the up vector and call it a day. And then we can use the line update function in the very same way that we used it for our interior domain, right? And once we've done updating it, we of course have to set the updated line, the updated first line to our channel in order to be consumed by our neighbor in the next iteration, right? So T is the iteration counter. Okay, and that's it. We don't create additional ghost zone layers within our data structure. We just allocate the memory that's needed in our partition. There's no explicit ghost zone in the code. It's the channel that handles this ghost zone exchange, right? And the logic is then within the iterator, and that's where the beauty of the templates come in, right? If I would have for the grid, I have a completely different data structure because I have it. I have some sparse matrix or whatever, but the boundary exchange is using a standard vector, right? But the iterator interface stays the same, right? It always stays the same. So I just replace the iterator here. So the return type here is a new type. It isn't the same type as if I would just dereference the current iterator, right? So it's a very nice abstraction to deal with boundary layers. So you don't have to allocate and remember, so, okay, I have an offset, and okay, so am I in the interior, blah, blah, blah. So the usual things, right? So I think it's a very lean way to formulate this. And the boundary exchange with your lower neighbor is symmetric to that. You just get your missing last row, right? And replace and create the bottom boundary iterator. And once you're done once you're done with updating your very last line, you send it to the channel so that your lower neighbor can consume it in the next time step. Okay. And that's it. That's my attempt to write a fully distributed version of a 2D stencil using higher level abstractions and not dealing with any explicit communication. So again, the full code is linked here. So I think the serial version had about 87 lines of code, and the distributed version, that distributed version, I think has 280 or so, including comments. So it's not a far stretch. I think it's a decent result in terms of the amount of code you have to write. If you run the example by yourself, the default problem size that I set in the program options is pretty small. It's 1,000 times 1,000, so not a lot of things to compute. So you might want to, if you try the example out and play with it a little bit, you might want to consider increasing the problem size using the --nx and --ny command line options. In that example, we use, as mentioned, striping in the y direction. So, as mentioned, it's not the best partitioning scheme, but it's easy for demonstration purposes. If you do scaling runs, you might want to take that into account to not increase the boundary exchange size too much. Right. Well, how good does it scale? Let's see in the next sessions. Thanks. Any questions?
You're not going to tell them how well it scales.
Not yet.
I'll make them wait.
I'll make them wait.
See you then.